Mathematical induction. We're going to prove by mathematical induction that 2 to the power of n is strictly greater than n for all positive integers. Our first step is prove that it's true for n equals 1. That's our base case. Second step is prove that it's true for n equals k, where k is a positive integer. Then the tricky step is prove that it's true for k plus 1. That's our inductive step. Finally, we simply state, by mathematical induction, it's true for all n. Let's do the first step, n equals 1. Let's change those n's to 1's. And if you look at that, 2 to the power of 1 is, obviously, strictly speaking, greater than 1. Second step, assume that it's true for n equals k. That's it. That's all we have to do for that step. Then, we prove that's true for n equals k plus 1. This is the hard bit. Now this is where we want to get to. 2 to the power of k plus 1 is strictly greater than k plus 1. So I'll put that at the bottom so we know where we're going. So what is 2 to the power of k plus 1? Well, we want to make use of our assumption that it works for 2 to the power of k. So let's get a 2 to the power of k in there. What else do we need? Well, 2 to the power of 1, because that's how powers work. 2 to the power of k plus 1 is 2 to the power of k times 2 to the power of 1. So our next step is, well, 2 to the power of k we assume to be strictly greater than k. So we can substitute that in, times 2. We don't need the power of 1. We could swap those around if you like. Now we still want to get that 2 times k looking like the bottom there, k plus 1. How do we do that? Well, if we split them apart, we could make them equal to k plus k. That's starting to look a little bit closer to it. Now let's have a look at that second k. What do we know about that? Well, it's at least equal to 1. So we could write greater than or equal to k plus 1. So if 2 to the power of k plus 1 is greater than k plus k, which is greater than k plus 1, and we have that strictly greater than in there, then we know that 2 to the power of k plus 1 is strictly greater than k plus 1. And that's our answer. That's exactly what we've been looking for. So we've proven it. Now we simply state by mathematical induction it's true for all n. Now you might be wondering, how can we assume it's true for k, then use that to prove that it's true for k plus 1? That sounds like circular referencing. Well, we proved that it's true for n equals 1. So we could simply say k was equal to 1. Then we could assume it's true for k because, well, k is equal to 1 and we know it works for 1. We proved that it's true if k equals 1, that it is true for k plus 1. Now if it's true for k plus 1, then it must be true for 2. Then we could simply say, well, now that we know that it's true for 2, then we could let k equal 2. And seeing that k works, we know that k plus 1 works, so it must work for 3. We could do this forever. And so then it's true for all n. So now we've proved by mathematical induction that 2 to the power of n is strictly greater than n.